This last question is also tricky because it starts mixing in different distributions. Okay, so the number of vehicles entering a parking lot varies from 5-minute interval to 5-minute interval. So basically, imagine you're standing at the gate of a parking lot and you take a timer and you time 5 minutes. You see how many cars enter in that 5 minutes. Okay, so that's what it's talking about. It says on average in a 5-minute chunk, 10 cars will come. Additionally, 30% of these cars are Japanese in make. Okay, so that's fine. What is the probability that 14 cars enter the parking lot in a given 5-minute period? Okay, so here my rate of success is in terms of 5-minute periods. I'm being asked about a 5-minute period. I don't have to reparameterize. I expect 10. Okay, so here, if there is, what is the probability of exactly 14 in 5 minutes? Okay, then I can just say this is a Poisson with the expected rate being 10. Okay, so I'll go to Calc, probability distribution, Poisson. Here I expect 10 in 5 minutes. What's the exact probability that I see 14 instead of the expected 10? Okay, so about 5% chance that I see 14 instead of 10 in a 5-minute period. B says, suppose 14 vehicles did enter. Okay, then assuming that each model of the 14 is independent, then what's the probability that 4 of them are Japanese? Because you have to really think about this for a second. What's happened is they said they measured a 5-minute period and 14 cars really did come. So we know the number of cars that came. Now, if these cars are independent of each other, then what's happening? Really what's happening here is now we have a fixed number of repeats. We know that number of reps is 14. The probability of being Japanese was given up here. It says 30% of cars are Japanese and they're independent. This must actually be binomial, not Poisson. The number of reps is known. So what's the probability of exactly 4 of the 14 being Japanese? Okay, this is just Z is equal to 4. It's 14, choose 4, 0.3, which is the probability of success to the power 4, and 0.7, which is the probability of failure to the power 10. In Minitab, then, this is just calc. Probability distribution binomial. Here, the number of reps is 14. Probability of success is known to be 30%, and the exact probability of having 4 out of those 14. Again, equal sign is this first option, the probability sign. Okay, so you can see the binomial probability of 4 out of those 14 being Japanese is somewhere around 23%. C, how many of the 14 vehicles would you expect to be Japanese made? Okay, so this is the expected value of out of 14. Okay, so this is the expected value of a binomial. Okay, again, go back to your binomial notes. The expected value of a binomial distribution is n times p. Here, n is 14, p is 0.3. 14 times 0.3, I expect 4.2 out of the 14 to be Japanese. What is the standard deviation? Again, for the standard deviation of a binomial, it is root n times p, 1 minus p. Okay, so n, of course, is 14, p is 0.3, 1 minus 3 is 0.7, I take the square root of it, plus or minus 1.7 expected to be Japanese. Okay, so what this is saying is if I take this expected number, 4.2, and add and subtract 1.7, then what I'm saying is in between 2.5 and 6-ish cars I would expect to be Japanese. Okay, if I had to say one number, I would say 4.2 are expected to be Japanese, but somewhere in between 2.5 and 5.9. What does D ask for? How many vehicles would you expect to enter the parking lot in a 30-minute interval? Okay, so you have to think about what's going on now again. Okay, now we're saying if we just stood at the opening of the parking lot and waited for 30 minutes and counted the number of cars that came in, how many do we expect? Okay, so what distribution is this? We have to think about it. What things are possible? Okay, well, it could be 0 cars, 1, 2, 3. Actually, it could be all the way up to an infinite amount of cars or close to an infinite amount of cars that come into the parking lot in 30 minutes. This is going back then to a Poisson distribution. I do not have a certain number out of, but I have a given rate, and then I have a time allotted. Okay, so here I'll have to reparameterize a bit. Okay, we were given information when we had 5-minute intervals. We had 10 cars in every 5-minute intervals. Here then, if I made it to a unit, so that's 10 out of 5, so 10 divided by 5, that would give me per unit. And then multiply by 30, because I want it in terms of 30 minutes. 10 times 30 divided by 5 will be, we expect 60 cars per 30 minutes. Okay, the other way of thinking about it is, how many 5-minute chunks go into a 30-minute period, and you can just multiply 10 by, it would be 15 5-minute periods in a 30-minute chunk. So you could do 10 times, sorry, not 10 times 15, what's 30 divided by 5? There would be 6 5-minute chunks in a 30-minute period. So it would be 10 times 6. Or 60 cars. Either way, you could find out that we would expect 60 cars in a given 30 minutes. Okay, so D is asking for the expected value of a Poisson distribution. Here, the expected value of any Poisson distribution is just lambda. Lambda here was that we expected 60 cars in 30 minutes, so we would expect 60 cars in 30 minutes. The standard deviation of a Poisson is the root lambda. Okay, so the variance of a Poisson is lambda. So the square root of lambda, or square root of 60, would be 7.7. Then in 30 minutes, we would expect 60 plus and minus 7.7 cars to enter the parking lot. So in between 52 and 68-ish is how many cars we would expect in a 30-minute period.